Okay, this is the second video of probably 3 videos dealing with side links and areas and surface areas and volumes, little shortcuts that we can use in order to go from one of those qualities to the next. Let's finish or start with what we finished with last time. We talked about with an area of a two-dimensional shape, if I know the ratio of the side links, then all I have to do is square that ratio, square the numbers in order to get the ratio of the areas, right? So let's do the same thing here with surface area. That's the point of video 2 here. So I want you to draw a rectangular prism. Don't draw that one. Let's ignore that one. Okay, I started to draw that and realized how long it was going to take me to draw the bigger one. Let's say I have a rectangular prism here. So it's 5 blocks by 2 blocks by 1 block. I want you to copy that down. I have another prism with a scale factor of 2. And when I say a scale factor of 2, all I'm saying, I abbreviate it as SF. The scale factor is 2. That means that I doubled each side length. So 5 became a 10. 2 became a 4, and instead of 1 unit tall, it's 2 units tall. Let's talk about the surface area of this shape. If I counted up the areas of the surfaces, the front face would have an area of 2. I have a back that's 2 as well. So I got 2 plus 2 for the front and the back. The left side has 1, 2, 3, 4, 5 units of area, and the right side has 5 units of area too, so I'm going to go ahead and add 10 more for the left and the right. The top has an area of 10, and the bottom would have an area of 10, so that's 20 total. And if I added all those up, that means the surface area of this shape would be 34 square units. Now, the question is this. We already learned that it's not just, hey, listen, if we double the side lengths, it does not double the area. It doubles, if you double with the area with two-dimensional shapes, we know if we double the side lengths, we would take 2 squared, we would have 4 times as much area. That's the conclusion we drew last time. The question is this, do we get the same thing here? If we have a scale factor of 2, do we take 34 times 2 squared to get the new surface area? That's the question. Is this relationship going to hold? Well, let's figure out what that is first. 34 times 4, 2 squared. Is this surface area 136? That's what we want to know. So let's go through and let's figure it out. I would have the left and the right face would have 20 boxes. So I have 20 on the left and 20 on the back side. That's 40 total. The front and the back have 8 boxes per side. So 8 on the front, 8 on the back. That's 16 total. And the top and the bottom have 40 boxes each. So I have 40 on the top and 40 on the bottom. That's 80 total. If I take 80 and 40 and 16, those do indeed add up to 136. So, the conclusion that we can draw is this. If we know the ratio of side lengths, let's say that it's m to n, then we can conclude, yes, we can conclude, well, shoot, I'm not even right where you can see it. If the ratio of side lengths is m to m, it turns out that even the ratio of the surface areas is m squared to n squared. So one more example, real quick off to the side. I'm just going to have a triangle here and a triangle here. Okay? Let's say that this triangle has a height of 4. This triangle has a height of 16. This triangle has a base of 8. And this triangle has a base of 32. Here are the 2 steps in order to figure out, listen, I know that the area of this is 1/2 of 8 times 4, half of 32. The area of this triangle is 16. I could go through and I could do this the long way by doing 1/2 base times height, or this is what I want you to understand. I went from 4 to 16, that's 4 times as big. I went from 8 to 32, that's 4 times as big. These triangles are proportional. If the side lengths are multiplying by 4, if the scale factor is 4, that means the area factor, if you want to call it that, would be 4 squared. That's 16 times as much area. So I take the original area of 16. It's 16 times as big. The new area is going to be 16 times 16, which is 256. There's a different way to work it, in other words. So here's one more example. Ready? The diameter of a soccer ball is about 8.75 inches. The diameter of a tennis ball is about 2.5 inches. So how many more times surface material is needed to make the outside of a soccer ball when compared to the tennis ball? Well, here's what I know. If I take the big number and divide it by the little number, that gives me something, okay? The diameter of the two is what I'm comparing. That's 3.5. It's 3.5 times bigger across. So that means in order to get to the area, or the surface area, I take 3.5 and I square it. You take 3.5 and you square it. That means you have 12.25 times as much surface area. How many more times surface material is needed? 12.25 times the surface material. Hopefully that makes sense. We've got one more video coming up. It's about volume.